Hello, we're continuing with life science and cell biology in a nutshell. We're learning about the consistency of the cell membranes, which are made up largely of phospholipid molecules interacting with protein molecules. So we learned that the most abundant membrane lipids are the phospholipids that have a polar head group, as well as two nonpolar hydrocarbon, aka fatty acid tails. The tails are can differ in length depending on what fatty acids the phospholipid molecules contain. They're usually between 14 and 24 carbon atoms in length. The fatty acid tails are. So the phospholipid molecule, which has a glycerol backbone, and on one side the two fatty acid tails, which are nonpolar, and on the other side a phosphate group and choline, which are the polar and the polar head group of the phospholipid molecule. So you have two fatty acid tails. Usually one fatty acid is unsaturated, which means that it has a kink, and aka a double bond, a cis double bond, making it unsymmetrical, um, and the molecule not being straight. So it has a skew on it. This gives the membrane the ability to be more fluid and not to pack too tightly together and become a solid. So it gives it a little more flexibility, the cell membrane. And the other fatty acid molecule is just not kinked at all. It's just a linear hydrocarbon chain, and this is called a saturated fatty acid, so there's no kink. So this is what the diagram looks like. So you have oxygens in red, shown in red, and the phosphate in green. So this is what the phospholipid molecule looks like. The nonpolar and the polar head group, and the nonpolar tail. So an example of phospholipid molecules, phosphatidylcholine, schematically here shown, and the space filling model. The kink results as a result from the cis double bond. So each double bond creates a kink in the tail. The differences in the length and the saturation of the fatty acid tails are important because they influence the ability of the packing of the phospholipid molecules with each other, and the fluidity of the membrane is determined. The shape and the amphipathic nature of the lipid molecules causes them to form bilayers spontaneously in an aqueous environment. So hydrophilic molecules generally dissolve readily in water because they contain charged groups. So if they contain either charged groups or uncharged polar groups, they may interact favorably with the water molecules or even hydrogen bond. However, molecules which are hydrophobic are insoluble, and because none of their atoms are charged, so they are nonpolar, so they have unfavorable interactions with water. If dispersed in water, they force the adjacent water molecules to reorganize into cage-like structure surrounding the hydrophobic molecule. So here you have a polar molecule as an example, acetone, and which has polarity because it has an oxygen group, and water, which is H2O. So the polarity of the acetone causes it to disperse evenly within the water and interact in a favorable way. However, 2-methylpropane, which is not polar in its structure, does not interact easily with water. It forces water molecules to reorganize. Um, so this compound, 2-methylpropane, is virtually insoluble in water. So where there's no polarity, there's no real interaction between the molecules. So usually partially negative and partially positive molecules attract one another, or parts of molecules, or atoms. So the hydrophobic portions of the amphipathic molecules cluster together. So two ways that the molecules pack, and if they're amphipathic, so we have the lipid molecules, they may pack forming a lipid micelle, forming spherical shape with tails inward and the head groups outward. So either way, the polar and the non-polar ends are in opposite directions, and it must interact with similarly polar molecules that are adjacent. So the bimolecular sheets or bilayers may form if it's like a sandwich shape being formed. In this case, a bilayer, with the nonpolar ends interacting with one another and the hydrophilic ends being exposed to where the water is. So bilayers are formed spontaneously due to the cylindrical shape of the phospholipid molecules. So if there may be any kind of gaps in the membrane, the same process of the fusion of intracellular vesicles, which have the same consistency of the membrane, will repair the membrane, and the membrane will close in on itself, forming a seal. So the closed structure of the bilayer is stable. It avoids water in some aspects and interacts with soluble molecules on the other aspect. So a living cell is created in this way, and the shape and the amphipathic nature of the phospholipid molecule in the cell are determined in this way. So the membrane structures functions are determined by the lipid bilayer and its amphipathic nature, and its fluidity is controlled as well. Around 1970, researchers first recognized that individual lipid molecules are able to diffuse freely within lipid bilayers. So bilayers may form from spherical vesicles called liposomes, which vary in size from about 25 nanometers to 1 micrometer in diameter. Black membranes are termed for a membrane where the partition or hole is filled between membrane sections. So phospholipid vesicles are called liposomes, and black membranes are ones that form across a small hole in a partition separating two aqueous compartments. They are used to measure permeability properties of membranes. Various techniques have been used to measure the motion of individual lipid molecules and across membranes. We'll continue in the next part. Thank you.